Have you ever wondered why the Moon, our closest celestial neighbor, doesn't have a global magnetic field? This question has puzzled scientists for decades and continues to be a subject of intense research. The Moon, a familiar sight in our night sky, may seem like a simple, barren rock, but it holds many mysteries. One of these enigmas revolves around its magnetic field, or to be more precise, its lack of a global one. A magnetic field, for those who may not be familiar with the concept, is like a giant force field that surrounds a celestial body. It's an invisible shield that protects the planet from harmful solar radiation and helps to maintain its atmosphere. Here on Earth, our magnetic field, known as the geomagnetic field, plays a crucial role in making our planet habitable. But when it comes to the Moon, things are a bit different. While the Earth is enveloped by a strong global magnetic field, our lunar companion lacks one. This doesn't mean the Moon is completely devoid of magnetism. In fact, certain regions on the Moon's surface do exhibit localized magnetic fields, but these are patchy and highly localized, far from the global magnetic shield that Earth possesses. Now, this lunar magnetic mystery takes an even more interesting turn when we consider the Moon's past. Believe it or not, studies of moon rocks brought back by the Apollo missions have shown that the Moon once had a stronger magnetic field. So the question then becomes, what happened? Why did the Moon lose its magnetic field? This absence of a lunar global magnetic field has significant implications. It impacts the Moon's ability to retain an atmosphere and protect any potential life forms from harmful solar winds and cosmic rays. So, what's the scientific reasoning behind the Moon's missing magnetic field? Let's unravel this lunar mystery. To understand the Moon's lack of a global magnetic field, we first need to comprehend why Earth has one. Our home planet, Earth, is wrapped in an invisible field of magnetic force. This magnetic field originates from the molten iron that churns within Earth's outer core. As the planet spins, this liquid iron moves and swirls, generating electric currents. These currents, in turn, create the magnetic field that extends out from the north and south poles, forming a protective barrier that shields us from the sun's harmful solar winds. This process of magnetic field generation is known as the dynamo theory. Picture a dynamo, a device that converts mechanical energy into electrical energy. Now, imagine Earth's core as a massive natural dynamo. The movement of molten iron within the core, driven by the planet's rotation, is like the turning of a dynamo's wheel. This motion generates electricity and, consequently, a magnetic field. Now let's turn our gaze to the Moon. Just like Earth, the Moon has a core. However, it's significantly smaller and composed of a different mix of elements, including sulfur and nickel, along with iron. Unlike Earth's outer core, the Moon's core doesn't appear to be molten, and it's not clear if it ever was. The Moon's slow rotation doesn't generate the same kind of dynamic movement required for a dynamo effect. Moreover, the Moon's core is not only smaller, but also cooler. These factors make it less likely to churn up the sort of vigorous magnetic field-generating currents seen within Earth's larger, hotter core. So in essence, while Earth's core is a hot, bustling kitchen, whipping up a protective magnetic field, the Moon's core is more like a quiet, cool pantry, unable to cook up the same kind of magnetic feast. Now that we understand Earth's magnetic field, we can delve into why the Moon's magnetic field is different. The Moon's core is key to understanding its magnetic conundrum. So let's dive in and unravel this lunar mystery. The Moon's core is a silent dynamo. Unlike the Earth's core, which is a bustling hub of magnetic activity, the Moon's core is relatively quiet. But why is that? Why doesn't the Moon's core generate a magnetic field like our very own planet's core? The Earth's core is composed of molten iron and other metals, which generate a magnetic field due to the dynamo effect. This dynamo effect essentially occurs when heat from the Earth's core creates convection currents, causing the molten metal to move in a circular pattern. This movement generates a magnetic field that envelops our planet, protecting us from harmful solar radiation. The Moon, on the other hand, is a different story. It's believed that the Moon's core is smaller and cooler than the Earth's. This means there's less heat to create the necessary convection currents. Without these currents, the Moon's core can't generate a magnetic field in the same way the Earth's core does. In addition, there's a theory that the moon's core is only partially molten. This partial liquidity could mean that the moon's core doesn't have enough movement to create a dynamo effect. If the core isn't moving enough, it can't generate a magnetic field. These factors, the size and temperature of the moon's core, as well as its possible partial molten state, are the reasons why the moon doesn't have a global magnetic field like Earth. They also raise fascinating questions about the moon's past and its evolution. All in all, the moon's core is a silent dynamo. It doesn't move and churn like the Earth's core, and thus it doesn't generate a magnetic field. This is a primary reason why the moon doesn't have a global magnetic field. The moon's core, unlike Earth's, doesn't seem to act as a dynamo, which is a primary reason for the absence of a global magnetic field. Despite the lack of a global magnetic field, the moon isn't entirely devoid of magnetism. Quite the contrary, in fact. Scattered across the moon's surface, we find localized regions of strong magnetic fields, a phenomenon that has puzzled scientists for years. These localized magnetic fields, or magnetic anomalies as they're often called, are stronger than anyone would expect from a body with no global magnetic field. Now, you might be wondering where these magnetic anomalies come from, and you're not alone. There are a few theories out there. One suggests that these anomalies could be the remnants of an ancient, now extinct global magnetic field. This theory posits that as the moon's interior cooled and solidified, it locked in remnants of this old magnetic field, creating pockets of intense magnetism. Another theory proposes a more extraterrestrial origin. It suggests that these magnetic anomalies were created by the impact of massive asteroids. These celestial smash-ups could have generated enough heat to locally magnetize the lunar surface. And yet another theory, albeit a less popular one, suggests that these anomalies could be the result of processes within the moon's crust itself, independent of any global magnetic activity. These magnetic anomalies add an extra layer of complexity to our understanding of the moon's magnetic history. They challenge our preconceived notions and push us to refine our theories. They are like pieces of a celestial jigsaw puzzle, each one holding a clue to the moon's magnetic past, waiting to be deciphered. But as mysterious and perplexing as these magnetic anomalies are, they are not an obstacle. Rather, they are a fascinating opportunity for discovery. They invite us to delve deeper into the moon's magnetic past, to unravel the secrets it holds, and to further our understanding of lunar magnetism. So, as we continue to explore these magnetic anomalies, we are not just solving a lunar puzzle, we are piecing together a part of our cosmic history. These magnetic anomalies, although puzzling, provide intriguing insights into the moon's magnetic past. So, why doesn't the moon have a global magnetic field? We've discussed a few theories that may provide an answer to this lunar enigma. Let's take a moment to recap them. First, we explored the idea of a non-dynamo core. Unlike Earth, the moon may not have a liquid core stirring up electrical currents, which are needed to generate a magnetic field. This theory is backed by seismic data from Apollo missions, providing a compelling explanation for the moon's lack of a global magnetic field. Next, we delved into the partially molten state theory. This suggests that the moon's interior might be partially molten, but not enough to create the kind of magnetic field we see on Earth. It's like having a battery, but with not enough juice to power anything substantial. Lastly, we touched upon magnetic anomalies. These are pockets of magnetism scattered across the moon's surface. These anomalies hint at a complex history of magnetism on the moon, but they don't constitute a global field. Each of these theories contributes a piece to the puzzle, helping us build a clearer picture of the moon's magnetic reality. But, as with any scientific exploration, there's always more to learn and discover. The importance of ongoing research and future lunar missions cannot be overstated. As technology advances, we're able to gather more precise data and test new hypotheses. Future missions to the moon will provide invaluable opportunities for scientists to study these magnetic anomalies up close and personal, further refining our understanding of the moon's magnetic field. In the grand scheme of things, studying the moon's magnetic field is not just about solving a lunar mystery. It's part of a much larger endeavor to understand the mechanisms that drive celestial bodies and their magnetic fields. Each discovery brings us one step closer to comprehending the intricacies of our universe. The moon's magnetic field, or lack thereof, remains a fascinating area of study, promising more celestial secrets to be